emerge from seemingly abstract mathematical rules and immutable constants. It's it's really one of the most profound questions we can ask about our universe, isn't it?
Absolutely. It touches on the very foundation of existence.
So, our mission for this deep dive is to take a stack of the most important sources and give you, our listeners, a shortcut, a way to get genuinely well informed on how the physical world, arises from this foundation of pure logic and number.
Mm.
We're going to focus on what we're calling a foundational trinity of concepts. The mathematical constant pi, or
Yep.
the fundamental quantum of action known as Planck's constant h,
Crucial.
and that all truly mind-bending principle of wave-particle duality.
And we're going to guide you through a really fascinating journey here. We'll kick things off by exploring the individual significance of each of these three crucial components.
Okay.
Then we'll see how they all sort of come together, how they synthesize into our most successful theories of reality, namely quantum field theory and the Standard Model.
Right. The big ones.
Exactly. And finally, we'll venture into the more speculative frontiers, theoretical physics, even philosophy, pushing into the big why behind these rules.
Really deep questions.
Precisely. Our goal is to illuminate this intricate and honestly elegant process of how the universe is built from its deepest, most fundamental blueprint, a blueprint of mathematical and quantum law.
Okay, let's really dig into this then. To grasp how matter is built, like you said, we first need to understand the universe's most fundamental tools and the underlying principles.
Absolutely. And we should start with pi, the constant of periodicity. Now, everyone knows pi is, the ratio of a circle's circumference to its diameter, roughly 3.14159.
Right, from school geometry.
Exactly. But its true significance in physics, well, it goes far beyond just circles. It's because nature itself is constantly doing things in cycles or rotations or waves. Think about planetary orbits, right? Or a swinging pendulum, or even light itself moving through space as a wave. All these cyclical phenomena inevitably involve pi in their mathematical description.
So it just naturally pops up everywhere there's repetition or rotation.
Precisely, and this foundational role is beautifully captured in Euler's formula E to the I equals cos x plus I sin x. It sounds complicated, but it's basically the ultimate mathematical recipe for describing any wave phenomenon.
The mathematical bedrock, as you called it.
That's a good way to put it. And because waves are everywhere, pi shows up in electromagnetism, like in Coulomb's law or the Biot-Savart law, especially when there's spherical symmetry involved.
So it's like pi is the universal wave language that nature speaks, and since the universe loves waves, pi pops up constantly. But here's where it gets really interesting. Its role in quantum mechanics. That seems unexpected.
It does, doesn't it? But quantum theory, at its very heart, is fundamentally a theory of matter waves. So pi isn't just, descriptive. It's baked into the very structure of quantum reality.
Baked in. How so?
Well, it emerges as a crucial normalization, constant in foundational probability distributions, like calculating the ground state of a quantum system. And it's also vital for Fourier transforms. These are the mathematical tools physicists use to translate a particle's description, say, between its position and its momentum. And they do that essentially by breaking down its quantum wave function into individual sine waves, which again involve pi.
Right, waves again.
Exactly. And the connection is so profound, it's really quite amazing. A recent analysis of the hydrogen atom's quantum energy levels unexpectedly yielded a classic 17th century formula for pi. The Wallace formula.
Wow, from hydrogen atoms.
Directly from the quantum structure of hydrogen. It just shows how deeply pi is embedded. And this then leads us naturally to the reduced Planck constant, h bar.
Ah, yes, h bar. I see that everywhere in quantum equations.
Right, and it's defined simply as h divided by 2. Now, this isn't just notation, not just making things look neater. That 2 factor is crucial. It converts a full cycle into an angle in radians.
Right.
And quantum states, they evolve according to the phase angle of their wave functions.
Yeah.
They sort of spin in an abstract mathematical space. So a quantum directly reflects that quantum action, the fundamental stuff happening, is intrinsically tied to rotation and phase evolution.
So pi isn't just circles, it's the constant of quantum spinning, almost.
That's a great way to think about it. It reveals a far more profound role for pi. It's setting the rhythm for the quantum dance steps.
Fascinating. So pi is dictating the rhythm of the universe's waves and quantum spins. But if everything is spinning and waving, what does that mean for the fundamental granularity or pixelation of reality? How do we get something solid out of all this?
Excellent question. And that brings us directly to the second member of our trinity, Planck's constant h, the quantum of action.
Right, the H.
So back in 1900, Max Planck was wrestling with a huge problem called black body radiation. Classical physics predicted something utterly absurd, the ultraviolet catastrophe.
Yeah, infinite energy at high frequencies, right?
Yeah.
Which clearly doesn't happen.
Exactly, it just didn't work. So Planck's solution, which was revolutionary, almost an act of desperation at the time, was to propose that energy isn't continuous. It's emitted and absorbed only in discrete packets, or quanta.
Like tiny little bundles of energy.
Precisely. And the energy of each packet, E, was equal to hf, where f is the frequency and h was this new constant he introduced. Its value is incredibly tiny, about 6.626 times 10 to the minus 34 joule seconds.
Vanishingly small.
Almost nothing. But the fact that h is not zero is arguably the single most important feature distinguishing our quantum universe from a hypothetical classical one. It literally defines the granularity or pixelation of reality.
So that's why reality isn't smooth, because of h.
That's the core idea. And look at its dimensions, energy multiplied by time. That's what physicists call action. So h is the elementary quantum of action. Think of it as the universe's fundamental price tag, or the minimum cost for any physical process to occur.
So no change smaller than h is possible.
Effectively, yes. It sets a fundamental limit. This constant, it sets the scale for the Heisenberg uncertainty principle, that famous trade-off in how precisely you can know a particle's position and its momentum simultaneously.
Can't know both perfectly.
Never. And h, or rather h bar, H2A, also dictates that particle properties like spin can only take on discrete values multiples of 8, for instance. This quantization is fundamental for the emergence of stable, structured matter. Without 8, everything would just smear out, atoms couldn't form, nothing solid could exist.
So Planck's constant is why reality isn't a smooth gradient, but made of tiny fundamental chunks or steps.
Okay.
But what about that truly perplexing idea, the third part of our Trinity, that fundamental things can be both a wave and a particle? That just seems contradictory.
It does, doesn't it? And that's the principle of duality.
Yeah.
The wave-particle nature of existence. The quantum revolution completely dissolved that old classical distinction. We used to think of particles as localized, discrete bits of matter, like tiny billiard balls.
Yeah, point-like things.
And waves as spread out, continuous things like ripples on a pond. Quantum mechanics revealed that every fundamental entity possesses characteristics of both. It's weird, but it's how the universe works.
How did we even figure that out?
Well, it came in 2 key steps. First, the Planck-Einstein relation, E equals hf. While Planck introduced quantized energy absorption and emission for black body radiation, it was actually Einstein in 1905, his miracle year, who made the truly radical proposal that light itself is composed of discrete light quanta, which we now call photons.
So light isn't just a wave, it's particles too.
Exactly. And the definitive experimental proof came from the photoelectric effect. Remember that? Light shining on a metal kicks out electrons.
Yeah, I remember that from physics class.
Well, classical wave theory couldn't explain it properly. It couldn't explain why electrons were ejected instantly, why their energy depended only on the light's frequency, its color, not its brightness, and why there was a minimum threshold frequency below which nothing happened, no matter how intense the light was.
The wave theory just didn't match the observations.
Not at all. But Einstein's photon model, where light is made of particles each carrying energy, EH, perfectly explained all of these observations. Bang, bang, bang. It was definitive proof for the particle nature of waves.
Okay, so waves can act like particles. What about the other way around?
Now that was the next giant leap. In 1924, a young physicist named Louis de Broglie had this monumental intuitive insight. His PhD thesis, basically. He reasoned, look, if waves can be particles, maybe particles like electrons should exhibit wave-like properties too.
That sounds even stranger. An electron wave?
It does. He proposed the de Broglie relation, OLS-HP, where phone is the wavelength, h is Planck's constant again, and p is the particle's momentum. Now, for macroscopic objects like you or me, or even a baseball, the momentum p is so large that the wavelength is incredibly tiny, completely undetectable.
Makes sense. We don't diffract going through doorways.
Thankfully not. But for microscopic particles like electrons, their momentum is much smaller, so their de Broglie wavelengths are comparable to the spacing between atoms in a crystal.
So you could potentially see the wave effect.
Exactly. And this was spectacularly confirmed just a few years later, in 1927. Davison and Germer in the U.S., and independently George Paget Thomson in the U.K., observed electrons diffracting off crystals, creating interference patterns just like waves would.
Wow. So electrons really are waves too.
Undeniably. It proved the wave nature of particles. And what's truly elegant here is that EHF and EP aren't really independent ideas. They're two facets of a single unified concept. You can actually derive one from the other using relativity for massless photons.
How does that work?
Well, for light, Einstein's EEP flow becomes EPC, since photons are massless. We also know EAFE and the wave speed CFO. If you combine EPC and EEF, you get PCHF. Then substitute FC, so PCHC. The C cancels, and you're left with PC, or EHHEP.
Nice.
De Broglie's genius was hypothesizing this relationship applied universally, even to massive particles like electrons. So Planck's constant H becomes this universal conversion factor, the bridge connecting the particle description, energy E, momentum P, and the wave description, frequency F, wavelength of everything.
So wave-particle duality isn't just some weird quirk. It's fundamental. Everything is both, all the time.
In essence, yes. It depends on how you measure it, what question you ask of it, but the potential for both is always there.
Okay, my head hurts a little bit, but I think I'm following. So if these fundamental entities are these weird wave particles, how do they actually coalesce? How do they form the concrete solid matter we interact with every day? What's the mechanism?
Right. This is where we need a more sophisticated framework. This is where quantum field theory, QFT, the architecture of reality, comes into play.
QFT, okay, I've heard of that. Sounds important.
It is arguably the most fundamental description of reality we have right now. QFT beautifully resolved that wave-particle paradox we were just talking about. It proposes that the truly fundamental entities aren't particles or waves in the classical sense. Instead, they're continuous quantum fields that permeate all of space-time.
Fields, like magnetic fields.
Sort of, yes, but quantum fields. Think of it like this. There's an electron field, a photon field, a quark field, and so on, existing everywhere, even in empty space.
Okay, fields everywhere. Then what are particles?
This is the central tenet of QFT. A particle is nothing more than a localized, discrete, quantized excitation, a ripple or vibration in its corresponding field.
A ripple. So an electron is just a ripple in the electron field.
Exactly. The field itself is the underlying, spread-out, wave-like entity. It can interfere with itself, it has wave-like properties, and its quantized excitation, this localized ripple, behaves like a particle. It's localized, discrete, you can count them.
Wow. So QFT unifies the wave and particle picture naturally. Matter is just quantized field ripples.
Precisely. Matter is the quantized manifestation of underlying fields.
Mm.
And crucially, going back to our Trinity, the constants pi and h are intrinsically hard-coded into the mathematical formalism of QFT. Things like canonical quantization inherently involve h is 2p, and often the imaginary unit which connects back to waves via Euler's formula.
Which involves pi.
Right. It shows that quantization, h, and periodicity, or wave nature, are embedded in the deepest layers of the physical laws from which these particles, these ripples, emerge.
So everything we touch and see is just a ripple. That's genuinely mind-bending to think about.
Oh.
Okay, if QFT is the sort of architectural style, what's the specific blueprint? What's the model for how everything is actually built, from those ripples to, us and the universe?
That detailed blueprint is the standard model of particle physics. It's essentially the practical application of QFT principles. It describes all the fundamental particles and forces we currently know with astonishing accuracy.
Often called the most successful scientific theory ever created, right?
It really is. It explains the electromagnetic, the weak nuclear, and the strong nuclear forces, basically everything except gravity, which is still the odd one out.
Okay, so what's in the standard model? What are the parts?
Broadly, there are two main categories of particles. First, the building blocks of matter. These are called fermions. Think of them as the quanta, the ripples in the matter fields.
Okay, fermions matter.
Right. They have a quantum property called half-integer spin. And critically, they obey the Pauli exclusion principle.
Ah, the exclusion principle. No two identical fermions in the same state.
Exactly. And that's absolutely crucial for chemistry and the structure of atoms. It's why electrons arrange themselves in shells around a nucleus instead of all collapsing into the lowest energy state.
Yeah.
It allows for complex structures, for chemistry, for life.
So that principle is key for stability.
Absolutely fundamental. These fermions are divided into two types, quarks and leptons. And they come in 3 generations, each heavier than the last. But all the stable matter around us, protons, neutrons, electrons, is built just from the first lightest generation.
And quarks and leptons, what's the difference?
Quarks feel the strong nuclear force. They carry a property called color charge. Not actual color, just a name. They're never found alone, always bound together in composite particles called hadrons, like the protons and neutrons in atomic nuclei. Leptons, on the other hand, like the electron, don't feel the strong force.
Okay, so fermions are the matter bits. What holds them together? What about the forces?
Those are mediated by the second category particles.
Hmm.
The bosons. These are the excitations, the ripples in the force fields. They carry the interactions between the fermions.
Got it. Bosons equals forces.
Yep. The most familiar one is the photon, the quantum of the electromagnetic field. It mediates electromagnetism, binding electrons to nuclei to form atoms, responsible for light, electricity, magnetism.
The everyday force.
Pretty much. Then there's the gluon. There are actually 8 types of them. They mediate the strong force, gluing quarks together inside protons and neutrons, and also holding the atomic nucleus itself together against the electric repulsion of the protons.
The strongest force, hence the name.
By far. And finally, there are the W and Z bosons. These are very heavy and mediate the weak nuclear force. The weak force is responsible for certain types of radioactive decay, like beta decay, and it's crucial for nuclear fusion processes, like those powering our sun.
So fermions are the bricks, bosons are the mortar holding them together. Seems like a pretty complete picture.
Almost. But there was a huge puzzle piece missing for a long time. A really critical piece. The Standard Model, in its purest, most symmetric form, initially required all these particles, fermions and bosons, to be massless.
Massless, but clearly things have mass, we have mass, planets have mass. How do they solve that?
Exactly. That was a major crisis. The solution is ingenious, and it involves the final crucial ingredient, the Higgs field and mechanism.
Ah, the famous Higgs.
The very same. The idea, proposed way back in the 1960s by several physicists, including Peter Higgs, and only confirmed experimentally in 2012, is that there's another field permeating the entire universe, the Higgs field.
Another field. What's special about this one?
It's a scalar field, meaning it just has a value at each point, no direction. Its quantum is the Higgs boson, which has spin 0, no. But the really crucial part is that unlike other fields which have zero energy in the vacuum, the Higgs field has a non-zero energy value everywhere, even in what we think of as perfectly empty space.
So empty space isn't truly empty. It's filled with this Higgs field.
That's the idea. And particles acquire mass through their interaction with this ubiquitous field. You can sort of think of it like moving through molasses, though that analogy is imperfect.
So more interaction equals more mass.
Exactly. Particles that interact strongly with the Higgs field experience a lot of drag or resistance as they move through it. That's what we perceive as inertia or mass. So they have a large mass, like the top quark. Particles that interact weakly, like the electron, experience very little drag and have a small mass.
And particles that don't interact at all.
They remain massless. Like
Yeah.
the photon, the carrier of electromagnetism, it zips through the Higgs field without noticing it.
So the Higgs field gives particles their heft. And finding the Higgs boson in 2012 at CERN's Large Hadron Collider.
That was the triumphant final confirmation. Finding that ripple in the Higgs field proved the mechanism was real. It was the missing keystone of the Standard Model. This Higgs mechanism is the crucial final step in the formation of matter as we know it. It endows particles with substance, with inertia. This allows them to slow down, clump together, and form stable structures. Protons, neutrons, atoms, molecules, planets, stars.
So it's not just assembly, it's this interaction that allows structure to form.
Precisely. It's tied to a subtle process called symmetry breaking. As the very early universe cooled, the Higgs field turned on, breaking a fundamental symmetry called electroweak symmetry, differentiating the electromagnetic and weak forces, and, in the process, endowing particles with mass. Without the Higgs mechanism, the universe would be a very different, likely structureless place. No stable atoms, no molecules, no galaxies, no us.
Okay, the Standard Model with the Higgs paints an incredibly detailed picture. It beautifully explains what matter is and how it forms from these fundamental fields and interactions. But it still feels like there are deeper questions, right? Why this specific set of particles? Why these particular forces? Why do the constants like pi and h have the precise values they do?
You've hit the nail on the head. Those are the questions that take us beyond the Standard Model into the speculative frontiers of physics. The Standard Model describes the how incredibly well, but it doesn't fully explain the why.
So this is where things get really wild.
This is where we push the boundaries of what we know or even what might be knowable. We enter the realm where physics and philosophy start to blur, debating the very nature of reality itself.
Okay, I'm ready. What's one of the most mind-bending ideas out there trying to answer that ultimate why?
Well, one of the most radical and debated ideas is the mathematical universe hypothesis, MUH, proposed by Max Tegmark.
The mathematical universe. What does that mean?
Tegmark posits that physical reality doesn't just happen to be described by mathematics. He argues that physical reality is a mathematical structure.
Wait, reality is math, not just explained by it.
That's the hypothesis. In this view, constants like pi and h aren't arbitrary values nature just happened to pick. They are intrinsic defining properties of the specific mathematical structure that constitutes our particular reality. Particles, forces, fields, they're all just inherent features within this grand mathematical object.
So forming matter is just features of the math.
From an outside perspective, yes. For us, as self-aware substructures living within this mathematical reality, we perceive it as a physical world evolving in time. But the hypothesis suggests the underlying reality might be this static, timeless mathematical structure.
That sounds incredibly abstract, like a modern version of Plato's ideas.
Exactly. It's a form of modern Platonism. Tegmark even goes further, suggesting that all mathematically consistent structures exist physically, forming what he calls a level 4 multiverse. Our universe is just one possible mathematical structure among infinitely many.
Okay, that's huge. What are the problems with that idea? It sounds hard to test.
That's the main challenge, its lack of easy falsifiability. How do you experimentally prove or disprove that reality is math? It bumps up against the limits of scientific methodology as described by Karl Popper. There are also potential philosophical issues, maybe even conflicts with things like Gödel's incompleteness theorems, depending on how you interpret it. But it's a profound idea forcing us to question our assumptions.
Definitely profound. Is there another equally deep idea, maybe coming at it from a completely different angle, not purely math, but something else?
Absolutely. A very different but equally profound perspective comes from the legendary physicist John Archibald Wheeler. It's his concept of it from bit, the participatory universe.
It from bit, what does that mean?
Wheeler proposed that information, fundamentally, is the most basic constituent of reality. Not matter, not energy, but information, the bit. He famously suggested that every particle, every field, even the space-time continuum itself, derives its very existence from bits, the answers to binary yes-no questions posed by acts of quantum measurement.
So reality is built from answers to questions, from observation.
That's the core idea.
Yeah.
Wheeler envisioned this as a self-synthesizing loop. The laws of physics, the it, allow observers like us to exist. These observers, through the act of measurement, asking those yes-no questions of reality, give rise to information, the bit. And this information, this collection of bits, in turn gives rise to physical reality and its laws, back to the it.
Wow, a cosmic feedback loop where observation creates reality.
In a sense, yes. It suggests the formation of matter isn't some event that happened only in the distant past, but perhaps an ongoing process of reality being co-created by the acts of observation. It connects directly to the weirdest parts of quantum mechanics.
Like the measurement problem, or the double slit experiment where observing changes the outcome.
Exactly. Wheeler's idea tries to put the observer and the act of measurement right at the heart of existence. In this kind of framework, fundamental constants like pi and h wouldn't be properties of math itself, but maybe fundamental parameters governing this vast cosmic information processing system, the rules of the query and answer game.
That's another completely paradigm-shifting way to think about it. Okay, those are two huge philosophical leaps. But what about theories that try to unify everything within a more, let's say, traditional physics framework? Theories trying to find deeper origins for matter and space-time themselves.
Yes, definitely. Physicists are actively working on these, often called theories of everything, TOEs, even though that's a very ambitious name. They aim to bridge the gaps in the standard model, especially incorporating gravity, and ideally explain why things are the way they are from more fundamental principles.
What are the leading contenders there?
Two of the most prominent, though they take very different approaches, are string theory and loop quantum gravity.
String theory, I've definitely heard of that one.
Right. String theory proposes that the fundamental entities aren't point-like particles at all. Instead, they are unimaginably tiny, one-dimensional vibrating strings.
So not ripples in a field, but vibrating strings.
Exactly. And just like a violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different modes. And these different vibrational modes are what we perceive as different particles. An electron is one vibration pattern, a photon is another, a quark is another.
So matter is music.
That's the popular analogy, yes. It's incredibly elegant because it offers a natural path to unification. Different vibrations of the same fundamental object give rise to all particles. Crucially, one specific vibrational mode naturally corresponds to the graviton, the hypothetical carrier particle of gravity. So it inherently includes gravity.
And where do the constants and particle properties come from in string theory?
They are thought to be determined by the geometry of space-time itself, specifically the shapes and sizes of tiny, curled-up extraspatial dimensions, that the theory requires usually 6 or 7 extra dimensions beyond our familiar 3 space and 1 time. So the music of the strings, the properties of matter, are dictated by the shape of this higher dimensional space.
Yeah. Extra dimensions. Okay, that's another layer of complexity. What about the other one, loop quantum gravity?
Loop quantum gravity, LQG, takes a very different path. Instead of starting with particles or strings in space-time, LQG starts by quantizing space-time itself.
Quantizing space and time, making them discrete.
Precisely. LQG proposes that space-time isn't a smooth, continuous background. At the incredibly small game, Planck scale, vastly smaller than an atomic nucleus, space-time itself is fundamentally discrete, granular. It's described as a network of interconnected loops or nodes, forming what are called spin networks, or spin foam. Think of space itself as being atomic.
So space isn't empty, it's this network.
It is the network. And in this framework, matter fields and particles aren't separate entities placed on this background. They are excitations or properties woven into this fundamental quantum geometry. They arise from the structure of the spin network itself.
So matter and space-time are inseparable.
Fundamentally inseparable in LQG. The properties of matter, the values of constants, would emerge from the relationships and structure within this discrete space-time network. Matter formation becomes intertwined with the very formation and structure of quantum space-time.
Two very different, very complex pictures aiming for the same goal.
They are. And neither is complete or experimentally verified yet. But what's remarkable, looking across all these frameworks from QFT to MUH for bit strings LQG, is this kind of meta-narrative, this progressive dematerialization of matter.
Dematerialization? What do you mean?
We started with classical physics thinking of matter as solid, tangible stuff. Then quantum mechanics turned it into probabilistic wave particles. QFT dissolved particles into excitations of non-material fields. String theory turns them into vibrations of abstract strings in extra dimensions. LQG weaves them into the fabric of quantum spacetime itself. And MUH, or it from bit, potentially reduce them further to pure mathematical structure and information.
So the deeper we look, the less material matter seems to become.
Exactly. The answer to how matter is formed really depends on the level of reality you're probing. But notice, through all of this, our foundational constants, pi and h, remain absolutely essential. Their role just evolves from describing the properties of substance to defining the rules of the underlying fields, vibrations, geometry, or even information processing. They bridge the concrete and the abstract.
Wow. We've taken an incredible journey today, haven't we? From the sheer ubiquity of pi and the universe's fundamental rhythms and wave mechanics,
The constant of cycles.
to the pixelation of reality itself, the granularity defined by Planck's constant h.
The quantum of action.
Then we navigated that really mind-bending concept of wave-particle duality.
Everything being both and neither.
All synthesized beautifully in quantum field theory, where particles are simply ripples, excitations, and underlying fields.
Matter from fields.
And finally, given their very substance, their mass, their inertia, by the all-pervading Higgs mechanism.
The crucial last step for structure. And looking back over this entire deep dive, you can really see that the formation of matter is this grand, intricate interplay. It's a dance between the timeless, logical language of mathematics, embodied so perfectly by constants like pi,
The rules of form.
and the fundamental, perhaps contingent, rules of interaction and change, quantified by constants like h.
The rules of action.
Exactly. And this interplay gives rise to our quantum reality, this dynamic world of fields and their quantized ripples, from which our stable, structured, tangible world ultimately emerges. It truly reveals a universe that appears, at its deepest detectable level, to be this profound and unified tapestry woven from mathematics, information, and quantum principles.
It really is staggering when you step back and think about that journey. From abstract numbers and invisible fields to the chair you're sitting on, the air you're breathing. What stands out most to you? And maybe more importantly for our listeners to ponder, what new questions does this whole picture raise for you about the very nature of existence itself?